All right. Might help if I plugged my little presentation clicker in. There we go. Okay. So what we're going to do today is, sort of continue on with our topics, obviously, of bridge engineering, but we're going to start to dig into one particular side of the equation. Remember, last time, in addition to going through the specification, one of the really big things that we discussed was the fundamental design philosophy that we're going to use for bridges, not just throughout the semester, but what we use for our specifications here in the United States. And that philosophy is this concept of Lrfd, the idea that we factor the loads based on their probabilistic uncertainties, and then we in turn also factor the resistances based on their probabilistic uncertainties. Because the idea of it is we don't look at things as binary, as they're either safe or they're not safe. We recognize that there's scatter associated not just with the loads, but with the resistance as well. So we try and tailor our load factors and resistance factors to achieve that uniform level of safety. And that's the whole concept behind what it is that we do in design. So what I'm going to do today, probably next week, and maybe even a little bit after that, is start to tackle one side of the equation, which is the loads. Okay? Now, a lot of what we're going to talk about today and for weeks to come is very superstructure neutral, if I should say. What I mean by that is a lot of this stuff doesn't change whether the bridge is steel, concrete, timber, aluminum, popsicle sticks. It doesn't matter, because a lot of the specification, the bridges are all subjected to the same traffic, so a lot of the live loading provisions are the same. So a lot of this will help you out regardless of what type of bridge you're designing. But like with all the discussions we've been having this semester, a lot of it's going to have that flavor towards steel. Again, because you can take pre-stressed and spend all semester learning about pre-stressed in there. Okay. Excuse me. All right. So let's talk a little bit about bridge loading. And if you've got any experience with structural engineering, you probably think of things in dead load and live load. To be a little more specific, and I've mentioned this before, I like to talk about things in permanent and transient fashions. Permanent being loads that are always there, transient being loads that move. Okay? And we will spend a lot of time discussing the live loads on bridges, because it's not complicated, but I would say it's intricate. So let's start off with some of our provisions in AASHTO. So some of this you had before you walked in here, and the rest of it you should have now. Okay? Now this discussion, like I said, of bridge loading is going to take a while. So we're going to make use of the following. So start off section 3. You all have that from last time. Section 3 was where we looked at the load combos. Remember that big table of load combinations? In section 3 is also just the definition of the loads themselves. So what is the live load that we use? What is the dead load that we use, and what have you? So that's going to be defined in section 3. Section 4 is about how do we actually go about structural analysis in the world of bridge engineering. Because don't get me wrong, we're still using the beam with the hinge and the roller and the shear diagram, shear and moment and all that. We're still doing that, but it's not so simple. Okay, there's a lot of three-dimensional characteristics we need to capture with our analysis. Imagine this table is a bridge, and I've got traffic going from one end to the other. I've got this live load placed on the bridge. I have to figure out where to place that live load this way and this way. And it's not easy. I mean, if you've got some curved and skewed 3D bridge out in space, I mean, there's no way that you are going to get, really accurate results without some sort of computational software or something like that. I mean, nowadays, folks who do bridges like that, I mean, they've got these three-dimensional finite element models, and they can model the whole thing and get all the stresses to the 0.01 KSI and what have you. But you need to understand the code and the provisions. And a lot of what we're going to talk about is just that, just the spec, the code and the provisions. All right. So far so good? Okay. All right. So let's start off with the easy part. Let's start off with the permanent loads, the loads that always sit still. In other words, the dead loads, okay? Now, we really have two dead load force effects that we need to consider for highway bridges, specifically the highway bridges that we're dealing with and the components that we're dealing with, and those are DC loads and DW loads. I mean, if we were looking at substructures, we might have loads, earth horizontal pressures, and things like that. But for what we're doing, DC and DW. So what's the difference? Okay, DC stands for the dead load of all the structural components and the non-structural attachments. In other words, the weight of the bridge, okay, the self-weight of the structure. DW is the dead load of the future wearing surfaces and utilities. So DW might be things like your asphalt overlay and your utility attachments and things like that. Why do we split them up into different categories? Well, it's the same reason we split all our loads up into different categories. There's more variability associated with these asphalt overlays and utility loads than there is the self-weight of the structure. So we apply different load factors. So we have to keep them separate. All right? So far, so good, but now I'm going to make it a little complicated when we talk about DC. Okay, like I said, DC's basically the self-weight of the structure. So the girder, the deck, the cross frames, if you've got stay-in-place formwork, all of that, that's all DC. But the big thing that makes DC a little funky or a little I guess you got to pay a little bit of attention to is this whole concept of stage construction. Remember, and I've brought this example up before, but you've got your bridge. Imagine that concept of stage construction. You set the beams, erect your cross frames, set your formwork down, lay your rebar out, start pouring your concrete. All those loads have to be supported by the steel beam by itself. But once the structure becomes composite and you put something like the barrier or other attachments on there as well, that's not resisted by just the steel. That's the steel plus the concrete. You got to take care when you're computing these loads, that you're using the right section properties and applying the right loads to the right sections. Now, what we do when we're talking about DC is we use a particular naming convention, DC1 and DC2. So DC1 stands for the loads that go on first. In other words, the loads that are applied to the non-composite steel section. DC2 are the loads that are applied to the composite section. Since those loads are permanent and they're always there, we apply those to the long-term composite section. Remember that? Remember the difference between the short-term section and the long-term section was the deck got smaller, and we said that we needed a long-term section because that section represented, the concrete's loss of capacity over time. These loads are always there. There's always a barrier on the bridge and what have you. So does everybody understand the difference? All right. I wanted to take time and talk about the section properties first, because if I didn't, as soon as I got here, I've got to go into this big tangent and explain what's going on with the section properties. So I thought it was a pretty good idea to talk about all that stuff first. Now we're kind of speaking the same language with a lot of this terminology. Okay, so far so good? All right. Okay, now one other thing I should point out, and I guess I should have included it on this slide, and you're more than welcome to put it in your notes, but maybe it's a good thing I didn't, because now I can pop quiz you. DW. You think DW belongs on the short-term composite section or the long-term composite section? Long-term, it's always there. It's permanent. So if you want, you can put the little note there on the bottom that DW, it belongs on the long-term because it's always there. Right, so far, so good? Okay. Now, transient loads. Transient loads are a little tough. I mean, one of the first things we got to figure out is what exactly are we even designing bridges for? I mean, do you think we're really designing highway bridges in the United States to hold up Honda Civics? I say that flippantly, but I'm being serious. I mean, don't get me wrong. We could argue about the volume of traffic, and I don't know if any traffic engineer would stand up and say I'm completely wrong, but I'd argue at least in terms of number of vehicles, most of the vehicles on the road are passenger vehicles. But in terms of load magnitude, it's not even close. When you design a highway bridge for its structural capacity, you get the cars for free. Bridges don't even notice your Honda Civic or your Hyundai Elantra or your Toyota Tacoma. They don't even notice those loads. Those are feathers compared to the loads that really matter. Okay? What I mean by the loads that really matter are trucks, you know, truck loading. That's what really matters. Okay? Does that make sense? You know, cars don't really matter in the world of structural design of bridges. They're just not heavy enough. Now, when I say trucks, what I really specifically mean, and this is where we're getting a little bit into the terminology, are what I'm calling exclusion vehicles. You know, those sort of not very, very common loads, but those ones that are really, really heavy that bridges do experience from time to time. Things like concrete mixers, you know. I mean, imagine what's going on with a concrete mixer. A very significant heavy load in this one small area. Make sense? Okay, so concrete mixers, short haul vehicles. I've got concrete mixers on there twice, so that's a typo. I'm basically talking, I think I meant to put on there tractor trailers, so whoops. So I wanted to emphasize the concrete mixers. Yeah, I really wanted to emphasize it. Again, what's my, I think I'm allowed 7 mistakes this semester. Is that what it is? Is it 7? What's that? I'm on 9? Ooh, man, I'm in the red. All right, so when we're talking about the truck traffic that matters, we're talking about those exclusionary vehicles that produce extreme effects on the structure, okay? Now, that raises a question. Do we have to design for every single possible exclusion vehicle that's ever going to be on a bridge? No, you know. Now, what AASHTO does is they have developed a load model that we are allowed to use that represents what I'll call the statistical maximum live load that a bridge sees. You know, on average, this load model that we're going to see represents, on average, the maximum live load that a bridge will see. Again, there's variability, which is why we apply those load factors. We call this live load, we call it the HL93. Okay, we call it the HL93 because it's the highway vehicular live load, and it was developed in 1993. We're really clever, us engineers. All right. Now, let me talk to you a little bit about the HL93. The HL93 is not it's not an incredibly unique creation. If you go back into the history of bridge engineering, what we used to use for our live load model, I got the handouts up here. You can go ahead, Graham. What we used to use for our vehicular load model was case 1 or case 2 type analysis, and it consisted of either this vehicular truck model, which was called the HS2044, or this lane load. Over time, what happened was the loads that highway bridges saw kept getting heavier, and our loads really didn't catch up. Okay, that's what's going on here on this graph. So what's going on here on this graph is you've got 2 graphs, one on the left, one on the right. Now the one on the left is basically showing you what was happening with the bridge code, the specification, before we adopted Lrfd. And before we adopted Lrfd, we were using this load model that was developed, you know, HS2044, it was developed in 1944, okay? And what was happening was this. So here on the y-axis, what's being plotted is what's called a moment ratio, okay? So if I have a moment ratio of, let's say, 1.1, that means that the bridge is seeing 10% more moment than what we're designing it for. You see what I mean? So this was bad, you know. We were dealing with, you know, moments that were 80% more than we as engineers were computing. That's bad, okay? Because over time, the loads that those highway bridges were seeing were just, they were heavier, okay? So when we started to recalibrate the load model, we said, well, is there a way that we can incorporate this? And we said, well, how about this? Instead of doing the truck or the lane, why don't we do the truck and the lane? And that's basically long and short of what you're getting on the right. It's not perfect, but it's a whole heck of a lot better than we had before. Okay? All right. Make sense? All right. So this is just sort of a justification for what we're doing and why we're doing it. The load model that we're using has been calibrated to represent as best as feasibly possible, trying to keep the analysis as simple as possible. This load model represents, as best as possible, the maximum statistical likelihood of loads that we will see on highway bridges in the United States. Will you see this vehicular load model in, say, the Eurocode? Probably not, because it's Europe. They see different truckloads than we do. So just something worth mentioning, okay? I would argue that this model is very regionally based. Okay, so this is the moment effect. This is the same thing with shear, sort of same story. Okay, again, that red line is a moment or shear ratio of 1, where the model and the actual data that we're getting from the field are the same. Okay, and if you look in section 3 of your spec, you'll see these graphs. I pulled these directly from the spec. It's not like, I had to hunt for these things. Okay, so the dead loads are pretty straightforward, just all the weight of the structure. What specifically does the HL93 consist of? The HL93 consists of either the truck and the lane or the tandem and the lane. So let's take each of these one at a time. What is the lane load? The lane load is a uniformly distributed load that's equal to 640 pounds per foot, or 0.64 kips per foot. And where we put that lane load and where it goes, we'll talk about that here in a little bit. Okay. The design truck and the design tandem. What's going on with those? Okay. So here's the design truck. And if you took me for structural analysis in undergrad, you probably saw this before. We looked at this briefly, I think. I don't think we spent a significant amount of time on it. But this is the vehicular live load that we use for highway bridges in the United States. It is a triaxle truck. We've got 3 axles. The front axle weighs 8 kips. The 2 rear axles weigh 32 kips. I got a pop quiz for you. All right. Remember how I said HS2044, the HS20? If this axle weighs 8 kips, how much does each wheel weigh? What about here? What's 4 plus 16? That's where that comes from. Yeah. No. This axle is 32 kips. Now, that's just off the image. We're saying 2 wheel lines. So I see what you're saying. But when you're getting into I'll say this, when you're getting into that level, like if you were actually doing a full-blown 3D computer model, AASHTO will tell you how to apply that load. It will say that this, let's say this front wheel of 4 kips, must be applied over a 10-inch by 20-inch area. That's the contact area. So you would calculate your pressure and then put that on your finite element model, or if you're doing this 3-dimensionally. Okay. So far, so good? All right. Now, a little bit of a history lesson. Just to, sort of give you some additional clarity as to what's going on. Now look, don't get me wrong. This tandem load is primarily meant to represent just concentrated heavy loads that bridges might see, but there might be another reason for that. Why did the interstate system get created? Why? For a place, but okay, so you're talking about a place for airplanes to land, but I'm talking about a more general. No, if you go to Florida and areas like that, near Air Force bases or what have you, you'll find patches of the interstate where they make it a point not to have overhead lighting because they want a particular airplane lane. But my point is that the interstate system was primarily started as a defense program. In other words, rapid evacuation. and also transit for military vehicles. What do you think that represents? Possibly. Got a very heavy concentrated load on the road. A tank. What's that? Tank. When it's World War III, I don't think we're going to care. I don't think we're going to care when it's World War III. No, but this is just intended to simulate other very heavy loads. I mean, anybody who's worked at the DOH or any owner agency has dealt with permitting issues where they've got some construction project and somebody needs to transmit some massively heavy turbine or something across the interstate, and it's a very heavy concentrated load going down the road. Very, very, very possible. But military vehicles, concentrated heavy loads of transportation, any of those could be represented by the tandem. All right. So going back to the load model, it's either the truck in the lane or the tandem in the lane. Okay. Now, okay, so where can you find that? Article 3612. We're actually going to open the spec here in a little bit, and we're going to start to sift through a lot of this, and then we'll sort of identify where this comes from. One thing I will say, if you open the spec and then try and, go line for line through the spec and see if I'm going line for line in the spec, I'm not. I'm actually sort of hopping around all over the place with the spec because there's a difference between the way things should be organized in a specification and the way they should be taught the first time. So I am hopping around a little bit, but I'm doing it because I think it's the easiest way for you all to pick up what's going on. So if you turn pages a lot the first time you're doing this, that's okay. You kind of get used to it. All right. Now, the truck in the lane and the tandem in the lane will, by and large, work for just about every loading scenario. And when you got to look at it like this. When you're on some committee and your job is to write a specification and you're supposed to come up with a set of rules and provisions that apply to every single conceivable bridge that there is in the United States of America, that is not an easy task. Okay? It's tough. Okay? And what happens is we bridge engineers, and this is just a rule of engineering in general, we try and keep it simple as much as we can. And the load model that's been presented works most of the time pretty well. There are some instances where it falls short, and specifically those are around negative bending regions. Remember, if you have a two-span bridge, those end and middle spans, smiley face, but then around the pier we have frowny face, negative bending region. The one place that this load model kind of falls a little short is around those negative bending regions. It's just not quite enough load there. So, excuse me. So we have a sort of special load case that we have to do anytime we have a bridge that has a negative bending region. Okay? So what we end up doing is we end up putting two trucks on the bridge spaced at a particular interval. And I've got some pictures that kind of draw this out here in a little bit. Okay. So when we're dealing with live load, I would argue we've got four cases we really need to analyze. We've got the truck and the lane and the tandem in the lane. Now when we use, or the truck, or the truck, the design vehicle and the design lane, or this negative investigation. In this negative investigation, we do 90%. So I think these pictures will clear everything up. So here's case 1 and 2. What's case 1? The truck and the lane. This 3-axle truck with the front axle being 8 kips, the two rear axles, or the two axles at the back being 32 kips. Variable axial spacing. We put the truck and the lane on the bridge, try and get the maximum force response we can. I'm being a little vague with that because we're going to talk about how you do that very specifically here soon. All right? Bottom, the tandem in the lane. Now, pop quiz. This live load model on the top we've got a triaxial truck, but I'm sure there's a question probably brewing in some folks' heads. We've got this axial spacing that says anywhere from 14 feet to 30 feet. It's variable, okay? Now, it's your responsibility as the engineer to vary that to get the maximum force effect possible. Now, most software programs will do this for you. You don't have to, but I want to see if you understand what's going on. So let's just envision a scenario. Here's a bridge. I got a support here. I got a support here, okay? Now, let's say here's the truck. I can move that truck, up and down the bridge, it's transient. It can be wherever. Let's say I'm trying to generate the maximum possible bending moment that I can. I want this truck to produce as much bending moment as possible. Where would I put the truck? Would I put it over here? I'll put it over here. Maybe in the middle, right? That's going to make it bend as much as possible, right? And that's what that whole theory of influence lines taught you that you had way back when in structural analysis. Don't worry if it's been a while. We're going to cover it in detail. Okay, now that's the simple part. The axial spacing. If you're the engineer in charge of this project, would you put that axial spacing at 14 feet or 30 feet? 14. You want to lump those loads as close to the center as you can, right? Make sense? Okay, so yeah, it's variable spacing, but sometimes there's a little bit of logic that comes to that. Now, when we do fatigue loading, we keep it at 30 feet because that's just how the spec was calibrated. We'll talk about fatigue. Fatigue is its own animal. We'll talk about that later. Okay. Now, for the negative bending investigation, we take 90% of what you see here. We do a double truck investigation or a double tandem investigation. The deal with the double truck, we lock these at 14 feet, and we can put these these two trucks wherever as long as we maintain a minimum of 50 feet between them. Like we can't have them be 30 feet apart. They can be 300 feet apart, but they can't be 30 feet apart. They have to be at least 50 feet apart. For the two axles, anywhere between 26 and 40. Okay? And like I said, I know this is a little messy and there's all these distances that you got to go through. Again, put yourself in the position of a bunch of code developers that have to come up with a way of designing every single potential iteration of highway bridges in the United States. There's 600,000 bridges in the U.S. It's tough to come up with a single model that works for everything. Okay, this is pretty good considering. Okay. Any questions? Okay. I do want to talk a little bit more about these provisions before we get into an example. What I talked about before was the strength limit state and the service limit state. If we are talking about fatigue or deflections, a couple things. So fatigue, like I said, we keep that rear axle spacing at 30 feet. It just goes off the way the fatigue spec has been developed. So if you look at what a computer program will output for truck moments or fatigue truck moments, they're pretty close, but fatigue moments tend to be a tad bit less. When we do live load deflection checks, we use either the truck or 25% of the truck plus the lane. And that's just the code specified provisions for preventing maximum allowable exceeding maximum allowable deflection. So the truck or the 25% of the truck plus the lane. Okay. Lastly, I think this is basically our last concept. We got to talk about dynamics. You all like dynamics, right? Dynamics. You like dynamics? We're going to talk about dynamics. Don't worry, we're not doing any rotational momentum problems or anything like that. That's not what I'm talking about. All right? When we do live load analysis, we have to be realistic about things. And one of the parameters that we have to assess is the idea of dynamic effects. What I mean by that is when we do a structural analysis problem, there's a beam with 20 kips sitting at the middle, or, we just assume it's been there forever and that load is static. That's not how bridges experience loads. bridges see, trucks go on there very heavily. In other words, think about like, here's an example that's unrelated, but I think it'll make a lot of sense. Let's say I put 20 pounds on the table like that. Let's say I drop a 20-pound weight on the table. Which is going to have the worst impact? Dropping it, right? Because it's not about just the force, it's the fact that that force is producing a dynamic effect on the structure. Okay? Trucks run really fast, run across bridges. Not only that, I don't know if you've been in a car in the state of West Virginia, but there's these things called potholes. Have you heard of potholes? Yeah, everybody around here's heard of potholes. When you drive across a pothole, what happens to you? You go like that, right? What do you think happens to the bridge? Well, that load is shaking on the structure, right? That produces an amplification of the force effect, right? If you put a very heavy truck that's driving on a road where the surface is very rough, those loads can be amped up a little bit. So we take care of that through the use of what are called impact factors. That's why we've got this LL plus IM, the live load plus impact. That's what that means. All right. Most cases, we're going to use an impact factor of 1.33. And if you've ever had a course in structural dynamics or done anything with vibrations, that is an incredible simplification of a very complex phenomenon. There used to be these formulas that we would use to compute impact factors, and then future studies basically said, let's just keep it simple and use 1.33. So we use 1.33 for just about every limit state that we assess. We got two special cases for fatigue. We use 1.15 because the dynamic effect of that single truck is really not the biggest concern. It's the cyclic loading that matters for fatigue. Now with deck joints, the dynamic effects can be a little worse for them, so we bump that impact factor up a little bit. Okay. One thing, those impact factors are only applied to the truck and the tandem, to that vehicular component. That lane load, we don't amp that up at all. So this slide right here, this is one I would put a big star on, because this one slide is going to help you out in doing your calculations later. Just about everything I think you need to know in terms of your load computations for the live loads are going to be right here. So when you're dealing with strength and service limit states, you got 4 load cases. You got the truck in the lane or the tandem in the lane, 100% of that, and see this 1.33? We're putting that impact factor on the truck and on the tandem, okay? That special negative bending investigation where you got to do the double truck and the double lane, or the double truck and the double tandem, we have 90% of all of that. Again, applying the impact factor only to the vehicle, not to the lane, all right? Fatigue limit states, we just use 1.15 times the fatigue truck. And then for live load deflection, we either have the truck or 25% of the truck and the lane. Again, that impact factor thrown in. Okay? Now this might all be kind of vague because we haven't talked about how to actually do the analysis. In other words, we've got all these nice, pretty equations, and this is simple, but we got to answer 2 things. Where do we put the truck this way? Longitudinal placement. Where do we put the truck this way? Make sense? Okay. Does anybody have any questions so far? Okay. All right. Let's see. What time is it? 7:05. Okay. I'm going to get us, this is what we're going to do. I want to just at least take a few minutes and pull up the specs so you can see where some of this stuff is coming from. And then I might introduce what we're going to do for the rest of the evening, which is we're going to take a representative bridge. In other words, the bridge that you all did your section property spreadsheet off of, and we're going to compute all the dead loads for it. It's not difficult, but it's detail-oriented. We need to go through and do all those calcs. So let me take a little bit of time and actually open up the spec for a little bit. So, okay. So what I'm looking at is section 3. Okay. So you all have this, right? All right. Now, first off, we looked at this last time, right? Those were the actual load combinations, you know, where we got the 1.75 times the live load and all that. I'm on 3411. I'm on page, what page am I on? Let me scroll. I think it's up here. 314. I'm on pi. All right. So I'm on 3-14, and then we got that. All right. If we go to the next page, that's where we got the permanent load factors and what have you. This is, you know, where those dead load factors come from. Let's see. Past that, some stuff on load factors for construction loads. I'm going to skip over that pretty quickly. I want to get into starting right here, 3.5. Okay, so this should be new. Permanent loads. Okay. Dead load shall include the weight of all components of the structure, appurtenances and utilities attached thereto, earth cover, wearing surface, future overlays, da-da-da-da-da. Okay? In the absence of more precise information, the unit weights specified in the table below may be used for dead loads. All right? What's the unit weight of steel? It's 490. I told my steel folks that there's one number I wanted them to remember. It was the unit weight. You got the 4 right. All right. All right. This is a table which outlines some of the unit weights of typical materials that we use for highway bridges in the United States. Now, if you're on a bridge project and you're working with a particular, let's say, manufacturer, and you need to know the unit weight, you probably will be able to, you know, if you've got some unique component, you'll probably be able to get the weight of it from the manufacturer. But if you're dealing with something like typical concrete or typical steel or some of these other materials, you can get the unit weights right here. And these unit weights, the units are kips per cubic foot. Okay? Now, two of the ones that I guess I would expect that you remember, which are pretty common, are number one, steel. The unit weight of steel. If you have a cube of steel that's 1 foot by 1 foot by 1 foot, it weighs 490 pounds. So 490 kips per cubic, or 0.49 kips per cubic foot. Okay? Now, concrete, you know, we've got here that normal weight, you know, regular old concrete weighs about 145 kips per cubic foot. What you probably ought to write to the side is that when we're dealing with reinforced concrete, what's our unit weight? Or what do we typically use for a unit weight? Anybody remember? One 150. All right. When we deal with like reinforced concrete, we tend to take this number and bump it up a little bit. We'll take it and bump it up to 150 or 0.15, and that accounts for the fact that when we got reinforced concrete, we've got concrete and rebar inside it. So we bump the loads up a little bit because there's rebar inside it. All right. But if there's anything else that you're not sure of, just look it up here. All right. So far, so good. Okay. Now, live loads. Okay. Now, some of this stuff we haven't talked about, and we will attack slowly. For instance, the number of design lanes. We didn't even talk about that. We will later when we get into transverse placement. You know, where do you place the trucks this way? You also have to look at how many trucks go on the structure. I mean, you know, if we're designing a highway bridge on Hal Greer, are you saying there's only one potential design lane? No, there could be two. There could be three. It just depends. Depends on the width. So, so there is that. We'll talk later also about multi-presence factors. And the idea about multiple presence factors is they're trying to account for the probability that you have coincident trucks on the bridge at the same time. A lot of the distribution factors that we'll use later have multi-presence factors built into them, but some of them we actually have to go out of our way and incorporate it. And there's a table right here that describes it, but we'll talk about that later. Okay? Now, this we have talked about. The actual vehicular live load consists of either the truck in the lane or the tandem in the lane, and that's what we've got in those 2 bullet points. We've got a bunch of commentary here. Well, by golly gosh gee, look at those graphs. We just looked at those graphs a little bit ago. So I don't think I really have too much to say about that. A lot of this specification development and actually organizing the spec was done by a very, very small group of really smart and capable engineers. One of them, unfortunately, he actually recently passed away. He was a professor at the University of Delaware. His name was Dennis Mertz. I met him a couple times. He's a really nice guy, so that's kind of a shame. Okay, looking at the actual design truck, you know, this is the same thing we looked at earlier. You know, the front axle of 8 kips, two rear axles of 32 kips, and we've got all the spacing there. The design tandem's just described. There was no pretty picture, so I threw a pretty picture in the slides for you. So I threw that in there for free. You didn't have to pay for that. That was a joke, not a very funny one. We've got our lane load described. Look right here. This is what I was talking about, this tire contact area, 20 inches by 10 inches. This is if you're actually going through and doing the full-blown three-dimensional model. And there's actually, for other trucks, there's ways of computing the tire width and length. Like if you've got the tire applying the load, you know, how can you compute that? So there's a lot of nifty stuff in the spec. I'm not going to worry about distributing load through earth fills and whatnot, or any culvert stuff. Now, this is this concept of application of the live load. This is where we have this discussion on the negative moment, or that special negative moment investigation, where you have 90% of the 2 trucks placed around the negative bending regions. I'm not going to sit here and read word for word. I'm not saying you should either, but you should make yourself familiar with some of this stuff. I mean, I haven't given you the entire spec. I've given you bits and pieces. You should at least be somewhat familiar with what's going on. If there's any one section of the spec right now that I think you should probably at least leaf through and make sure you're familiar with, it's 3.6, or at least the components of, I gave you all 3.6. I would look through 3.6. I'm not saying read it word for word, but at least be pretty familiar with it, because a lot of stuff we're going to do in the not too distant future comes from this. Excuse me. We have this discussion here on 330 of the fatigue load, and remember it's one truck with the constant spacing of 30 feet between the 2 rear axles. That's where all that comes from. Again, you look, I don't mean to bring up that bad, melancholy news, but you'll see this name Mertz quite a bit in the spec. He was pretty influential in its development. Some stuff later, which is pretty nifty, is this whole the ADT discussion, which I know my transportation folks have heard of ADT before, I've got to believe. But what we care about in bridge engineering is the average daily truck traffic, and not only that, but the average daily truck traffic that's within a single lane, okay? And that goes into our fatigue loading that we'll discuss later. Fatigue was all calibrated based on a single truck. So there are methods for taking ADT, converting it to ADTT, average daily truck traffic, and then converting that to average daily truck traffic for a single lane, which we'll talk about later. And it all depends on things like how many lanes are available, are you dealing with an urban interstate, a rural road, or what have you. Okay. Any questions about any of this? I mean, I'm not going to get into rail transit or anything like that. We've got our dynamic impact factors that you see on 3-33. That's pretty much all I really need to talk about for the purposes of our discussion here. Anybody have any questions about any of this stuff, about any of these code provisions? I really think that looking through 3.6 is probably pretty pertinent, because here's the reason why I say that. I don't expect you to know every single line and every single sentence out of 3.6, but I do want you to become familiar, because later on, when we talk about 610, which is the section in the spec for steel I-beams, I mean, we really are going to dissect that section with a scalpel. Okay, there's a lot of stuff going on in that section that we need to have a really good handle on. So being familiar with a specification is probably pretty important. I think it would personally be a good exercise on your part to take the lecture notes and then the code and see, am I able to find where he's getting all this stuff? Okay, that's important. Okay, it's also important when you all get out in your career. You know, you're not going to have a Dr. Michelson over your shoulder for every bridge that you design, but being able to negotiate the spec on your own is a very important task. All right. Anybody have any other questions? Okay. I tell you what. Let's go ahead and take a little bit of a break, but we'll come back here in a few minutes. What I want to do when we come back is, like I said, I want to take that bridge that you all did for your homework, and I want to calculate the dead load start to finish. Okay. Then what we're going to do is, well, then what you all are going to do, I mean, I've already got it, but you're going to do a similar exercise on this homework. I've given you a bridge, and I want you to compute all the dead loads for this bridge. So just to ensure that you all know what's going on. So far, so good? All right, say it's 7:17. What do you say, what, 7:30? 7:35? What's that? 8:30. Funny guy. Now I'm going to say 7:25. No, no, 7:30. Is 7:30 all right? All right, let's get back together here in a few minutes.